Hello everyone. So this is the next video on linear algebra. We started with the subspaces and we solved some problems on the subspaces. So let me recall what do you mean by subspace. See, if V is a vector space over the field F, then W is called a subspace of V of F. First of all, it must be a subset of V of F. If W is itself a vector space over F, then we say that W is a subspace. And we studied two verifications for this. One is one-step verification, other one is two-step verification. One-step verification is if alpha, beta are scalars, say W1 and W2 are from the subset W, then alpha W1 plus beta W2 must be in W. It's a single step verification. Two-step verification is if W1 and W2 are in the subset W, their sum must be in W. Second thing is if you scale that vector in W, that must be in W. So we solved this kind of problems. However, next I move on to what is the operations of subspaces, that is algebra of subspaces. First thing is intersection of any two subspaces is a subspace. That is, if W1 and W2 are two subspaces of V of F, then W1 intersection W2 is always a subspace of V of F. Their intersection will always a subspace. Or else in general, if you consider W1 intersection W2 intersection W3, still it's a subspace. You can generalize this. If Wi, I belongs to indexing set. Indexing set means it's an like your serial number. It starts with natural number. So then intersection of Wi, I belongs to I, is always a subspace, provided each Wi is a subspace. If this is collection of subspaces, then intersection is always a subspace. This idea is clear? First point we must note, intersection of any two subspaces is a subspace. Second thing is, what can you say about union? Union of two subspaces need not be a subspace, but it will be subspace if and only if one is contained in the other. Idea is clear? Intersection of two subspaces it will be a subspace, whereas union of two subspaces need not be a subspace. And it will be a subspace if and only if either one is contained in the other. If W1 is a subset of W2 or else W2 is a subset of W1, then you can claim that it's a subspace. Once we solve few problems, we'll be going to understand what exactly it conveys. Next thing is, what is a linear combination and linear span? See, for this, what is a linear combination? We have one identity which we use in number theory called Bézard's identity. What is this Bézard's identity? It says, see, 3 and 5 are relatively prime. So what else you can write? 3x plus 5y equals to 1. Idu gottide. Whenever the GCD is 1, you can write it as a linear combination of 3 and 5. which sums up to 1. Howda? Or else if P and Q are relatively prime, there exists integers x and y belongs to z such that P into x plus Q into y equals to 1. That means whenever the GCD is 1, you can write them as linear combination of x and y such that its sum equals to 1. This we know. Then what is this linear combination? Right? Of course, I don't want this right now, but however, to understand what is linear combination, see, V1, V2 vectors are there. I start with 2 vectors. What are the linear combinations? Linear combination, look to this. You take any scalar, alpha and beta. You take 2 scalars. And you just write alpha E V1 plus beta V2. Is it clear? Equals to 0. This is the linear combination of V1 and V2. Getting my point? This idea is clear. If V1, V2, V3 are there, then what is the linear combination of this? Alpha V1 plus beta V2 plus gamma V3 equals to 0. In general, if V1, V2, etc., Vn is a linear if this is the set, then what is the linear combination? Alpha V1 plus beta V2, or else alpha 1 V1, alpha 2 V2, alpha 3 V3, etc. Alpha n V1 equals to 0, where each alpha is a scalar. So this is the linear combination of these vectors. Then what is linear span? For this, look to this. You may ask me, sir, why I want to write alpha 1 here? I will choose alpha 2 here and alpha 1 here. Whether it is a linear combination? Yes, it's a linear combination. Then someone will say, no sir, I don't choose this. Let it be alpha 1. Instead of alpha 2, I will choose alpha n V1, V2 plus alpha n minus 1 V3 plus etc. alpha 2 Vn is 0. Whether this is the linear combination? Yes. You consider set of all possible linear combination likewise. In place of this, you take any scalar. Getting my point? Scalar into V1, some scalar into V2, scalar into V3, scalar into Vn equals to 0. Where these scalars are filled from? The field F. You consider set of all possible fellows of this kind. Then that is called linear span of V1, V2, etc. Vn. ಎಷ್ಟು ಸಾಧ್ಯತೆ ಇದೆಯೋ ಅಷ್ಟನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೋಬೇಕಿಲ್ಲಿ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ನೋಡಿ, ಇಫ್ ಐ ಕನ್ಸಿಡರ್ ಎನಿ ಫೀಲ್ಡ್, ಫೈನೈಟ್ ಫೀಲ್ಡ್ ತೊಗೊಂಬಿಡೋಣ, ಸೊ ಪಾಸಿಬಿಲಿಟಿ ಕಡಿಮೆ ಆಗುತ್ತೆ. If you consider finite field, there is, let me say, I am in ZP, which is a field where P is prime. See, look to this. If V1, V2, Vn is given, some scalar into V1, some scalar into V2, some scalar into Vn. So, how many members you can choose from this? Zp is there. 1, 2, 3 bar, 4 bar, up to P minus 1 bar. P bar is 0 bar. How many elements are here? P elements are here. How many elements you can choose this alpha? Alpha belongs to Zp. So there are P choices. How many choices for this? You can choose any one of these P elements. P choices. How many for this? P choices. That means totally how many choices? P cross P, P. How many times? N times. P to the power n choices are there. How many choices? P to the power n choices. That means if I write linear combination of V1, V2, Vn in the field Zp, how many elements I can write? I can write P to the power n elements. I can write V1 something or else I can write a vector like v1 plus something v2 plus something vn. This something has how many choices? As p to the power n choices. So I can write all the elements of this vector space by p to the power n linear combination. p to the power n linear combination ಬರಿಬೋದು ನಾನು ಅದನ್ನು. ಅರ್ಥ ಆಗುತ್ತಾ? I can write p power n times. That linear combination can be written p to the power n times. ಆ ಥರ ಎಷ್ಟು linear combination ಬರಿಬೋದು ಅಂದರೆ p to the power n times. ಆ ಥರದ್ದೆಲ್ಲ ಕಲೆಕ್ಷನ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಫಸ್ಟ್ ಎಲಿಮೆಂಟು ಇಟ್ಸ್ ಎ ಲೀನಿಯರ್ ಕಾಂಬಿನೇಷನ್. ಇದರಲ್ಲಿ ಏನೇನಿದೆ ಅಂದರೆ ಸಮ್ ಸ್ಕೇಲಾರ್ ಇಂಟು v1 ಪ್ಲಸ್ ಆಲ್ಫಾ 2 ಇಂಟು v2 ಪ್ಲಸ್ ಆಲ್ಫಾ ಎನ್ ವಿ ಎನ್. ಇದರಲ್ಲೂ ಅಷ್ಟೇ ಸಮ್ ಆಲ್ಫಾ 2 ಇಂಟು v1 ಪ್ಲಸ್ ಆಲ್ಫಾ 1 ಇಂಟು v2 ಪ್ಲಸ್ ಆಲ್ಫಾ ಎನ್ ವಿ ಎನ್. ಈ ಥರ ಎಷ್ಟು ಎಲಿಮೆಂಟ್ಸ್ ಇರ್ತವೆ? p ಟು ದಿ ಪವರ್ n ಎಲಿಮೆಂಟ್ಸ್. ಈ ಥರ ದೀಸ್ ಸೆಟ್ ಆಫ್ ಆಲ್ ಪಾಸಿಬಲ್ ಈಸ್ ನಥಿಂಗ್ ಬಟ್ ಲೀನಿಯರ್ ಸ್ಪ್ಯಾನ್ ಆಫ್ v1 etc vn where in the field zp. ಲೀನಿಯರ್ ಕಾಂಬಿನೇಷನ್ಗಳೆಲ್ಲದನ್ನೂ ಕನ್ಸಿಡರ್ ಮಾಡಿದ್ರೆ ಇಟ್ ಈಸ್ ಎ ಲೀನಿಯರ್ ಸ್ಪ್ಯಾನ್. ಸೊ ವಾಟ್ ಈಸ್ ಲೀನಿಯರ್ ಸ್ಪ್ಯಾನ್? ಲೀನಿಯರ್ ಸ್ಪ್ಯಾನ್ ಅಂದರೆ ಇಟ್ ಈಸ್ ಎ ಸೆಟ್ ವಿಚ್ ಕಂಟೈನ್ಸ್ ಆಲ್ ಲೀನಿಯರ್ ಕಾಂಬಿನೇಷನ್. ದಿಸ್ ಅನ್ ಆಲ್, ಎಲ್ಲದು, ಆಲ್ ಪಾಸಿಬಲ್, ಎಷ್ಟು ಸಾಧ್ಯನೋ ಅಷ್ಟು. ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಅಸ್ ಲೀನಿಯರ್ ಸ್ಪ್ಯಾನ್. ಅರ್ಥ ಆಗುತ್ತಾ ಅದು? ಸೊ ನೆಕ್ಸ್ಟ್ ಥಿಂಗ್ ಈಸ್ this is a remark. Linear span of the set S is given by L of S and it is always subspace of the vector space. Linear span of S is always a subspace of a vector space. Getting my point? Second remark. If S is any set, any non-empty set, then L of S is the smallest subspace that contains S. ಅಂದರೆ ಇದರ ಅರ್ಥ ಏನು? ಸೊ S is a subset of vector space. Then linear combination of S means definitely S is always contained in L of S. ಅರ್ಥ ಆಗುತ್ತಾ? S is a subset of L of S. Now ಹೀಗಿರುತ್ತೆ. The scenario is this. This is L of S. And L of S is the smallest subspace that contains S. ಅಂದರೆ if W is any subspace, such that S is contained in W, then L of S is contained in W. Andre this will be W. So S is a subset. L of S is a subspace. It's always a subspace. S is contained in L of S, that you know. But however, S is also, W also contains S. But which is the smallest among W and L of S? L of S. This idea is clear. Andre L of S is smallest subspace that contains W. Idea is clear? Third observation. If S is itself a subspace, instead of considering the subset, you consider S is a subspace. Then what will be L of S? If this is a subspace, then L of S is nothing but S itself. The idea is clear? The idea is clear. That must be clear. See, I just summarize that. L of S is what? Set of all linear combination of this set S. and we already noted this is a subspace of vector space. If S is, this is for S is any subset. If S is a subspace, then L of S is yes, and L of S is the smallest subspace that contains S. This must be clear. And 1, 2, 3, fourth observation is, if we want to show L of S is yes, or else if we want to show L of S is equals to some W, then we will just check. See, we need to check this, right? L of S will be always contained in this. We will just bother about this. Artha agata? If you want to show, or else V antane, if I want to show L of S is V, whole vector space, how to show this? Already we know linear combination of all those span is a subset of V. Only our bothering thing is whether V is a subset of L of S. If this is clear, then we can say L of S is V. See, just to understand this linear combination, I will consider R square over R, and I consider S to be 1, 0 and 0, 1. So what will happen to L of S? See, L of S will be R square. How? However, L of S thing is this, and R square must be contained in L of S. What is L of S? Set of all linear combination of this S. How does that will look like? Let me consider alpha x and y belongs to R. These are scalars. So I will just choose this is V1 and this is V2. What is x into V1 plus y into V2? So x into 1, 0 plus y into 0, 1. That is equals to what? X comma 0 plus 0 comma y. That is x comma y. It's an real number. It's an real number. So it is a subset of R square. It's an ordered pair of real numbers. That means L of S is contained in R square. This is agreed. How about this? Whether R square is contained in L of S? How does R square will look like? X comma y, where x and y are real numbers. Whether R square is contained in L of S? That we need to check. So give me any element in R square. Can I write it as linear combination of? Yes, that is the point here. So x and y can be written as x into 1 comma 0 plus y into 0 comma 1. That is nothing but x into v1 plus y into v2, which belongs to L of S. So R square is contained in L of S. This implies R square equals to L of S. That's what I said to you. See, this is obvious. Only we need to bother about this. Idea is clear? That's what I was stressing out here. Kindly try to understand by looking into some examples. Then only you will get to know what's happening. This idea is clear. Yes. Next is, what is linear sum of two subspaces? Still we are in the operations of subspaces. We did intersection, we got the subspace itself, we did the union, we didn't get the subspaces because union of two subspaces need not be a subspace. Then we will try to add them. See, if W1 is a subspace of the vector space and W2 is any subspace of the vector space, then what is the sum? It is nothing but W1 plus W2, where W1 belongs to the subspace, and W2 belongs to this subspace. This idea is clear, and we can show that W1, W2 is a subspace of V of f. We can show this actually if I assume V1 and V2 belongs to W1 plus W2. V1 will look like, let me say, some gamma 1 plus gamma 2, and V2 will look like some delta 1 plus delta 2, where gamma 1 and delta 1 belongs to W1 and gamma 2 and delta 2 belongs to W2. Then what is alpha V1 plus beta V2? That is equals to alpha gamma 1 plus gamma 2 plus beta into delta 1 plus delta 2. This is equals to alpha gamma 1 plus beta delta 1 plus alpha gamma 2 plus beta delta 2. But this belongs to what? Since W1 is a subspace already, alpha gamma 1 plus beta delta 1. So gamma 1 and delta 1 are already in W1. So this belongs to W1. Since W2 is a subspace and these two belongs to W2, alpha into some element of W2 plus beta into element of W2 belongs to W2. So this belongs to W1 plus W2. So W1 plus W2 is always a subspace. That is called linear sum of two subspaces. And we have one more identity here, that is W2 are just subsets. If they are just subsets, then what is W1 union W2? This notation is nothing but linear span of W1 union W2. L of S can be written as this also. This symbol stands for linear set of all linear combination, that is linear span of S. So this stands for L of linear combination, set of all linear combinations of W1 union W2. If they are just the subsets, it is nothing but L of W1 plus L of W2. If they are subspaces, then same thing, W1 union W2 is L of W1 union W2. It is L of W1 plus L of W2. Once they are subspaces, linear span of a subspace is the same subspace. Linear span of subspace is subspace. So if they are subsets, it's L of W1 plus W2. If they are subspaces, it is nothing but the linear sum itself. This idea is clear? You must be clear with these things. Then if S is contained in T, this implies L of S is contained in L of T, and we already noted this. It is L of S plus L of T, provided they are subsets, where S and T are subsets. If they are subspaces, then L of S union T is S plus T. That must be clear. This idea is clear? And S is a subspace of V of F if and only if L of S equals to S. Thank you. We will just think about, after this we will try to think about linear dependence and independence. Then we solve basis and dimension. That concludes the first chapter of linear algebra. Thank you so much.